So rotations and rotational symmetry are another type of transformation, and we're going to see there are actually some links between rotations and rotational symmetry and what we just saw, reflections and line symmetry. So in order to get an idea of what's going on, I've got 4 regular polygons on the left, a regular triangle, which is an equilateral triangle, a regular quadrilateral, which is otherwise known as a square, a regular pentagon, and a regular hexagon. And what we have to do is imagine rotating these. I will have a dynamic example of rotation a little bit later on using GeoGebra, but for now we just have to use our imagination. So there's 2 things that we're going to talk about with respect to rotation, and that is order of rotation and angle of rotation. And they're related. If you know one, you can figure out the other, and we'll see what that relationship is. So if we took something that had no rotational symmetry at all, like a human face, and we started rotating it through a full circle, full 360 degrees, there would only be one time in that full rotation when it would appear identical to its starting point, and that would be right at the very end. And so that would have an order of rotation of 1, and the angle of rotation would be 360 degrees. But these shapes I've got on the sheet here, they will appear identical if I rotate it around the center point more than once. And that's the order of rotation, is how many times will it appear identical as I rotate it through 360 degrees. So in fact, that triangle, if I rotate it 120 degrees, it will appear identical. And if I rotate it another 120 degrees, it will appear identical. And finally, if I rotate it a third 120 degrees, it will appear identical. And so the order of rotation for this triangle is 3, and the angle of rotation is 120 degrees. A square, all you need to do is rotate it 90 degrees. You can imagine just tipping it on its side. And if you're rotating it around the center, it would appear identical. And we can do that 4 times through a full rotation, and every time we're rotating it 90 degrees. Now, a pentagon, you would have to rotate a little bit less than 90 degrees, and you can do it 5 times, and the angle turns out to be 72 degrees. And a hexagon, you can rotate it 6 times. And again, you can just imagine sort of rolling it onto each side as you move around the hexagon. And the rotational angle would be 60 degrees. Now, you can see the relationship here. If we take 3 and we multiply it by 120, we get 360 degrees. Similarly, if we take 4 and multiply it by 90, we get 360. And so this is why if you know one, you can always find the other. So the order of rotation and the angle of rotation must multiply to give you 360 degrees. And so really, in some sense, 1 is sufficient. You know all the information you need by just knowing either the order of rotation or the angle of rotation. Now, I said there was a link between this and line symmetry. So the order of rotation for this triangle is 3. And as we saw last time, there are 3 lines of symmetry. And for a square, the order of rotation is 4. And we didn't look at a square last time, but a square has 4 lines of symmetry. Didn't draw that one very well, but there are 4 lines of symmetry for a square. And similarly, for a pentagon, there are 5 lines of symmetry. You can imagine going from any vertex to the opposite side. Which one am I missing here? There we have 5 lines of symmetry, and so on. So the number of lines of symmetry that an object has is similar to the order of rotation. Now, let's take a look at the dynamic example. So I've set up this page on GeoGebra that allows you to rotate an object around a point. So again, just like we saw with line symmetry and then we moved into reflections, there is the reflection is a transformation, and once you do a reflection you have line symmetry. Well, here it's a little different, right? We have the ability to rotate an object around a point. Now, we're not going to have the same sort of demonstration of rotational symmetry unless that point is the center of the object, and we can experiment with that a little bit later. But let's just take a look at what's going on here. So for instance, if I move this red point P, which is the point of rotation, right into the center of the square, well, now I'm doing the rotation, and I can see that if I start at 0, I can rotate this 90 degrees, and I end up with it matching up perfectly. And then another 90 degrees would be 180, and it would match up perfectly. And then another 90, I'm going to be at 270. And then finally at 360, it'll be identical. So that's an examination of what we just looked at, which is the rotational symmetry of an object. But in this case, we can do a little bit more. So if we have a point outside the object and we want to rotate the object around that point, in the same way that with reflections, we have an object and an image, same is true with rotational with rotations. So the labeling here you have to pay attention to. It's A, B, C, D. The image is A prime, B prime, C prime, and D prime. So what's going on? Let's take a look at the rotation by 180 degrees, because you could just look at this and say, well, it's a reflection through a line. But in a way, a rotation by 180 degrees is a double reflection. It's a reflection through both the vertical and the horizontal line that pass through P. So if you draw a line between A and A prime, the midpoint is going to be P. The same between D and D prime, the same between C and C prime, and B and B prime. So the lines between those points are all the same. That's not true for other rotations, like rotations of 90 degrees. But you can see that AC, which is a horizontal line on the original, becomes, actually that's a little bit hard to see, but actually AC are opposite. So DC starts off as horizontal, and where does DC end up when we rotate by 90 degrees? DC ends up on the left as vertical. So all horizontal lines become vertical when you rotate by 90 degrees, and all vertical lines become horizontal. Now, for the most part in this section, we're only going to be looking at rotations of 180 degrees, but let's change the object that we're rotating a little bit. All right, so if we change the object so it's a little bit more irregular, if you like, now we can see that the object is not just a reflection, it is truly being rotated. And if you were looking at an object and its rotation, it's a little bit difficult if the angle is something other than 90 degrees or 180 degrees. If it's 90 degrees, it's a bit of work, but we can figure out the distances, both horizontal and vertical, from the point to, let's say, point A to the point of rotation. And then we can imagine rotating those around 90 degrees. All the horizontals would become vertical, all the verticals would become horizontals. If it's anything other than 90 and 180, though, it's pretty tricky, and the math gets a little bit complicated, so you'll have to save that for a later grade. But 180 degree rotation is fairly straightforward, right? Again, it's kind of like a double reflection. We're reflecting it through both a horizontal and a vertical line that pass through the point P. And you can see, if you draw a line from A to A prime, the midpoint is P, and the same for all the other points and their images.